Tonight, we uncover the unsettling possibility that the void currently surrounding you is not empty at all, but a seething reservoir of power waiting to be unleashed. Right now, as you sit in the quiet of your room, you feel a sense of absolute stillness. Your coffee sits motionless in its cup, the air is calm, and the walls around you appear solid and dependable. But this domestic tranquility is an illusion created by your senses, a necessary filter for your survival. In the time it took you to hear these first few sentences, you and everything you have ever known have traveled roughly 60 miles through the darkness of space. You are currently moving at 1.4 million miles per hour toward an invisible gravitational attractor, yet you feel nothing. More disturbing still is the fact that the nothing in the room with you, the empty space between your eyes and this screen, is currently being pierced by trillions of invisible particles and a vacuum energy so immense that it contains more potential than all the stars in the sky combined. If this is nothing, then why does it feel so heavy? If the universe was born from a vacuum, we are not just standing on the edge of a mystery, we are currently drowning in it. If you enjoy deep investigations into the hidden mechanics of our reality, subscribe now. The investigation begins with the stillness of your own home. Look around the room you are in right now. Focus on the space between the objects, the gap between your hand and the table, the air between the floor and the ceiling. To your eyes, this space is a mere backdrop, a passive stage upon which your life unfolds. For over 1,000 years, this was the established truth of our species, dictated by the Greek philosopher Aristotle. He taught that nature abhors a vacuum, a concept known as horror vacuum. Aristotle argued that a true void was not just impossible, but logically incoherent because space required substance to define it. If you were to remove everything from a box, the air, the dust, every single atom, Aristotle believed the universe would collapse inward to prevent such a hole in reality from existing. This was not just a philosophical debate, it was a psychological anchor for humanity. We needed to believe that we were surrounded by something, that the fabric of existence was continuous and full. You can test this ancient fear yourself with something as domestic as a drinking straw. When you place your finger over the top of a straw and lift it from a glass, the liquid stays trapped inside, seemingly defying the law of gravity. To the ancients, this was proof of the universe's desperation. They believed the water remained in the straw because the alternative, a vacuum forming at the top, was so offensive to the laws of nature that the cosmos would rather suspend gravity than allow nothing to exist. If you suck the air out of that same straw and block the end, the walls will collapse inward, as if the weight of the entire world is trying to crush that tiny pocket of emptiness. For centuries, we mistook this pressure for the universe's will. We believed the vacuum was a monster that nature fought to keep at bay. This intellectual ceiling remained unbroken until the year 1643, when an Italian scientist named Evangelista Torricelli decided to stop theorizing and start measuring. Torricelli took a long glass tube, filled it to the brim with heavy silver mercury, and clamped his finger over the open end. This is not speculation, this is the moment the modern world began. He turned the tube upside down and submerged the end into a basin of mercury before releasing his finger. In a world ruled by Aristotle, the mercury should have stayed in the tube, held up by the universe's fear of the void. But instead, the heavy liquid began to slide downward. It fell until it reached a height of about 30 inches, and then it stopped. Above the silver line of the mercury, there was now a gap. It was an airless, silent space that had been captured inside the glass. Torricelli had done what the greatest minds for a millennium said was impossible. He had created a vacuum. He hadn't just found a trick of physics, he had revealed that nothing could be weighed and measured. This is a credibility anchor for our investigation, the vacuum is not an abstract idea, but a physical reality. Torricelli realized that the mercury stayed in the tube because it was being balanced against something else. He wrote a phrase that should change the way you feel the air against your skin right now. We live at the bottom of an ocean of air. Just as a deep-sea creature is unaware of the crushing weight of the water above it, you are currently unaware of the 50 miles of atmosphere pressing down on your shoulders. The reason the straw collapses when you suck the air out is not because nature hates the void, but because the ocean of air is trying to push its way back in. Torricelli's experiment showed that the atmosphere has a specific weight, and the vacuum he created was simply a place where that weight had been temporarily pushed aside. But a deeper, more disturbing question emerged from that glass tube. If the air had been removed, what was left in the gap? You might be tempted to say nothing, but that is where our intuition fails us. Shortly after Torricelli, a philosopher and mathematician named Blaise Pascal took this experiment further. He realized that if we truly lived at the bottom of an ocean of air, then the water should get shallower as we climbed. He had his brother-in-law carry a mercury tube to the top of a mountain in France. As he climbed higher, the level of mercury in the tube dropped. The ocean was thinning out. This realization was the first step toward the edge of our world. It meant that if you kept going up, eventually the air would run out entirely. The Earth is not a world sitting in a sea of air. It is a tiny, fragile speck of dust floating through a vast, silent, and inhospitable void. Nature does not abhor a vacuum. A vacuum is nature's default state. The air you breathe, the clouds you watch, and the blue of the sky are just a thin, temporary skin stretched over an infinite abyss of nothing. Scientists in the 17th century began to study this nothingness with a growing sense of unease. They placed ringing bells inside glass vacuum chambers and watched as the sound faded into a ghostly silence. Without air to carry the waves, the sound simply ceased to exist. But here is the complication. Although they could no longer hear the bell, they could still see it. This is a vital detail. If sound requires a medium like air to travel, then light must require a medium too. They concluded that the vacuum wasn't empty after all. They believed it was filled with a mysterious, intangible substance called the luminiferous ether, a light-carrying fluid that permeated all of space. For nearly 200 years, this was the consensus. We believed the universe was full of this stuff, an invisible fabric that connected the stars to your eyes. But in 1887, two American scientists named Michelson and Morley built a machine to detect this ether wind as the Earth moved through space. They expected to see light traveling at different speeds as it fought against the current of the ether. They measured it with a precision of 1 part in 100 million. This was not a guess. It was the most high-tech experiment of its era. The result was a total failure. No matter how they moved their machine, light always traveled at exactly the same speed. The ether did not exist. There was no invisible fluid. Light, as Albert Einstein would later prove, did not need a medium to travel. It could propagate through a true, absolute void. For a brief moment in the early 20th century, it seemed like the mystery was solved. The vacuum was finally truly empty. But as we peel back the layers of the nothing in your room, the reality becomes far more complex than a simple absence of air. As industrial technology advanced, we learned to harness the vacuum to power our world. Every light bulb in your home, every old television screen, and the vacuum tubes in early computers were only possible because we could create small, controlled pockets of nothing. In these airless environments, we could study the fundamental particles of matter without interference. We discovered the electron, the X-ray, and the structure of the atom itself by peering into the void. What we found there was not a peaceful silence, but a seething, restless energy that defies common sense. This is what the data says. and it is perhaps the most important insight of this chapter. At the smallest scales, it is physically impossible to ever truly have nothing. Werner Heisenberg, a young physicist plagued by hay fever on a lonely island in the North Sea, realized that the universe is built on a foundation of uncertainty. His uncertainty principle states that you can never know both the exact position and the exact speed of a particle at the same time. Think about what that means for a volume of empty space. If you try to say there is nothing in a box, you are claiming to know exactly how much energy is there. 0. You are also claiming to know exactly how it is moving. It isn't. But the laws of physics forbid this level of precision. If you look at a tiny interval of time, the energy in that space must fluctuate. It must jiggle. Like a borrower taking a loan from a bank and returning it before the auditor notices, the vacuum can borrow energy from the future to create particles out of thin air, provided they vanish again almost instantly. This is the quantum seethe. Even in the most perfect vacuum on Earth, even in the darkest reaches of intergalactic space, pairs of particles and antiparticles are constantly popping into existence, dancing for a trillionth of a second, and then annihilating each other back into the void. This is not speculation. It has been measured directly. In 1947, Willis Lamb measured a tiny wobble in the orbit of an electron, a wobble caused by the constant pressure of these virtual particles hitting it like cosmic turbulence. If the vacuum were truly empty, that wobble would not exist. But the peak in his data was clear. The nothing is alive. We have now reached the first major complication in our journey. If the space in your room is teeming with this hidden activity, then the nothing from which our universe was born was not a barren desert, but a sea of infinite potential. We are not the products of a random explosion in a void. We are the frozen remnants of a vacuum that once fluctuated so violently it birthed 100 billion galaxies. But where did that initial field, that seething floor of the universe, come from? If we are to answer that, we must move beyond the room, beyond the atmosphere, and into the first fraction of a second, when time itself had yet to be defined. The investigation continues. To truly understand why the seething activity in your room is so significant, we have to look back to a time when the very idea of nothing was considered a heresy against the laws of nature. For more than 2,000 years, the intellectual architecture of our world was built on a single, comforting lie: that space is always full. This belief was anchored by the Greek philosopher Aristotle, who argued that a vacuum was not merely difficult to find, but logically impossible. He believed that nature would fight with every ounce of its being to prevent a hole from opening in the fabric of reality. This wasn't just a scientific theory, it was a psychological shield. We needed to believe that we were surrounded by a continuous, supportive something, a cosmic substance that filled every gap and connected every atom. You can feel the weight of this ancient certainty the next time you use a simple drinking straw. When you place your finger over the top of the straw and lift it from your glass, the liquid remains trapped inside, hanging in the air as if the law of gravity has been momentarily suspended. To the ancients, this was not a trick of pressure. It was a demonstration of the universe's desperation. They believed the water stayed in the straw because the alternative, a vacuum forming at the top, was so offensive to the cosmos that the universe would rather hold up the weight of that water than allow a single cubic centimeter of nothing to exist. For centuries, every time a straw worked or a pump failed, humans saw it as proof that the universe was full. We mistook the crushing weight of our own environment for the universe's will. The man who finally broke this 1,000-year-old ceiling was not a rebel looking to topple empires, but an Italian mathematician named Evangelista Torricelli. In 1643, he devised what can only be described as a trick to deceive the laws of nature. Torricelli took a glass tube about 3 feet long, sealed at one end, and filled it to the very brim with mercury, a liquid so heavy and silver that it feels more like a molten metal than water. Mercury is 13 times denser than water, and its weight is the key to this historical pivot. Holding his finger firmly over the open end, Torricelli turned the tube upside down and submerged it into a basin of more mercury. In a world governed by Aristotle, the mercury should have stayed in the tube. If nature truly abhorred a vacuum, the heavy liquid would be held up by the universe's fear of the void. But as Torricelli released his finger, the silver column began to slide. It didn't fall all the way, it dropped until it reached a height of about 30 inches, and then it stopped, shivering in the glass. Above that silver line was a gap. It was an airless, silent, and absolute void captured inside a piece of human-made glass. Torricelli had done what the greatest minds for a millennium said was impossible. He had created nothing. This is our first credibility anchor in this investigation. The vacuum is not a philosophical debate. It is a physical substance we can weigh and measure. This is not speculation. It is what the data says. Torricelli realized that the mercury stayed in the tube not because nature feared the void, but because it was being balanced like a set of scales. He realized that the air around us, the very air you are breathing right now, has a weight. He wrote a phrase that fundamentally shifted the human perspective of our home. We live at the bottom of an ocean of air. Think about the implications of that sentence for a moment. Just as a deep-sea creature on the floor of the Mariana Trench is unaware of the thousands of tons of water pressing down on its body, you are currently unaware of the 50 miles of atmosphere pressing down on your shoulders. This ocean of air is heavy. It presses against every square inch of your skin with roughly 14.7 pounds of force. The reason the straw collapses when you suck the air out is not because nature hates the vacuum, but because the weight of the entire atmosphere is trying to push its way back in. Torricelli hadn't just discovered a void, he had discovered that the air itself is a physical substance, as real and as heavy as water. Shortly after Torricelli's discovery, a philosopher and mathematician named Blaise Pascal took the experiment to its logical and unsettling conclusion. He reasoned that if we truly lived at the bottom of an ocean of air, then, as we climbed higher, the water should get shallower and the pressure should drop. In 1648, he had his brother-in-law carry a mercury tube to the top of the Puy de Dôme, a mountain in central France. As he ascended the slopes, the silver line in the tube began to fall. The ocean was thinning out. This realization was the first step toward the edge of our world. It meant that if you kept going up, eventually the air would run out entirely. The blue sky you see out your window is not an infinite canopy. It is a thin, fragile skin stretched over an infinite abyss. Our Earth is not a world sitting in a sea of air. It is a tiny, lonely speck of dust floating through a vast, silent, and inhospitable void. Nature does not abhor a vacuum. A vacuum is nature's default state. Almost the entire volume of the universe is made of this emptiness. This is where the story takes a disturbing turn. As scientists in the 17th and 18th centuries began to study these small pockets of captured nothing, they noticed something strange. When they placed a ringing bell inside a vacuum chamber and pumped out the air, the sound faded into a ghostly silence. Without air to carry the waves, the sound simply ceased to exist. But here is the vital detail. Although they could no longer hear the bell, they could still see it. This creates a massive complication for our understanding of the void. If sound is a wave that needs air to travel, then light must also be a wave that needs a medium. Scientists concluded that the vacuum wasn't empty after all. They believed it was filled with a mysterious, intangible substance called the luminiferous ether, a light-carrying fluid that permeated all of space. For 200 years we were back to where Aristotle started, believing that the universe was full of something we couldn't see, an invisible fabric connecting the stars to your eyes. But as we discussed in the previous chapter, the Michelson-Morley experiment in 1887 proved that the ether did not exist. There was no invisible fluid. Light does not need a medium. It can travel through a true, absolute void. This realization briefly made the vacuum feel empty again, but it opened the door to a much deeper mystery. If the vacuum is truly empty, why does it have specific properties? Why does light travel through it at exactly 299,792,458 meters per second and not a centimeter faster? This brings us to the seething flaw of our modern understanding. As we developed the technology to create even more perfect vacuums for light bulbs and television screens, we stopped seeing the void as an absence and started seeing it as a structure. We realized that even when you remove every atom, every particle of dust, and every photon of light, you are still left with the quantum field. This field is the rules of reality written into the void. It is the background energy that allows particles to exist in the first place. This is established science. The nothing in your room is not a barren desert, but a sea of infinite potential. It is the ocean of air scaled up to a cosmic level, an invisible, heavy, and seething reservoir of energy that birthed the universe itself. But to understand how this nothing could contain the DNA of 100 billion galaxies, we have to look closer at the jiggling floor of reality. We have to understand why zero is not a stable number in the quantum world. The investigation is moving from the mountain tops of France to the subatomic scale, where the vacuum begins to breathe. In the next chapter, we will see what happens when the vacuum is squeezed so tightly that it begins to scream. We have established that the vacuum is a physical substance we can weigh, but to understand why the nothing in your room is currently vibrating with the power of 1 billion suns, we have to look much closer than Evangelista Torricelli or Blaise Pascal ever could. We have to descend from the scale of mountains and silver mercury into a realm where the very concepts of here and now begin to dissolve. For decades, the vacuum was seen as a silent, empty stage, but as our technology allowed us to peer into the subatomic architecture of reality, we discovered that the stage itself is alive. This is not a philosophical metaphor, this is established science. The nothing you see between your hand and this screen is actually a seething, restless ocean of potential energy that never for a single femtosecond sits still. The man who first glimpsed this restless floor of reality was a young German physicist named Werner Heisenberg. And he didn't find it in a state-of-the-art laboratory, but on a lonely, wind-swept island in the North Sea called Heligoland. In the summer of 1925, Heisenberg was suffering from a debilitating case of hay fever, his face so swollen that he fled to the island simply to breathe the salt air and escape the pollen of the mainland. In that isolation, while watching the sun rise over the rocky outcrops, he realized that the universe was not the clockwork machine Isaac Newton had described. He discovered that at the most fundamental level, nature is built on a foundation of inescapable uncertainty. This is the famous uncertainty principle, and it is the reason why a state of true nothing is physically forbidden in our universe. To understand why, imagine you have a perfectly empty box in your room, and you have the power to cool it down to absolute zero. In a logical, classical world, every atom and every bit of energy would eventually stop moving. The box would contain nothing because everything would be at rest. But Heisenberg showed that this is a mathematical impossibility. If a particle, or the energy field in that box, were to stop moving completely, you would know exactly where it is and exactly how fast it is going. 0. The laws of physics strictly forbid this level of precision. Because the universe cannot be certain, there must always be a residual jiggling, a minimum floor of energy that can never be removed. Even at absolute zero, the vacuum breathes. This brings us to the quantum seether, a phenomenon where the vacuum is not a void, but a bubbling soup of virtual particles. This is the point where the investigation turns from physics into something that feels like a cosmic magic trick. Heisenberg's equations show that energy and time are linked in a delicate balance. Because of the uncertainty in this balance, the vacuum is allowed to borrow vast amounts of energy from the future, provided it pays that energy back almost instantly. This borrowed energy manifests as pairs of particles and antiparticles that pop out of the void, exist for a trillionth of a second, and then annihilate each other back into nothingness before the universe has a chance to notice the debt. Think of it like a borrower taking a massive loan from a bank and returning it before the auditor even looks at the books. Right now, in every cubic centimeter of the air around you, trillions of these virtual particles are performing this frantic, invisible dance. They are not real in the sense that they stay around to be touched, but they are real enough to have a physical impact on the matter you can see. This is what we call quantum fluctuations, and they are the secret heartbeat of the cosmos. If this sounds like theoretical fantasy, you must look at the data from 1947, when an American scientist named Willis Lamb found a way to measure this nothing directly. Lamb realized that if the vacuum was truly a seething soup of virtual particles, those particles should be hitting the electrons inside atoms like microscopic turbulence. He looked at the orbit of a single electron and found that it was wobbling ever so slightly. This wobble, now known as the Lamb shift, was the proof we needed. The electron was being buffeted by the pressure of the vacuum itself. To understand the sensitivity of this measurement, imagine scaling up that electron's wobble to the size of an apple. If you did that, the vacuum chamber Lamb used would have to be scaled up until it was 100 times larger than our entire solar system. It would take light 40 days just to travel from the top of the machine to the bottom. Yet, even at that nearly impossible scale, the jiggle of the vacuum was there, clear and measurable. This is not speculation. When we calculate the energy of these fluctuations, the math matches the real-world experiments to 1 part in a million. The nothing in your room is effectively a high-pressure reservoir of energy that we are only just beginning to map. But here is the most unsettling detail of the quantum seethe, the one that links the stillness of your room to the birth of everything. We once thought the Big Bang was a chaotic, random explosion from a single point, but the seething nature of the vacuum suggests something much more structured. Our best theories now tell us that the entire universe is essentially a quantum fluctuation that was caught in a moment of runaway expansion. During the first fraction of a second of existence, a process called inflation took these tiny subatomic bubbles of the quantum seethe and stretched them across the sky. Those tiny variations in the nothing, the little overdensities and underdensities where a virtual particle had popped into existence, became the blueprint for the entire cosmos. They were frozen into space, becoming the seeds around which matter would later clump to form stars and galaxies. This is one of the most profound and beautiful ideas in all of science. Every galaxy we see, including our own Milky Way, began its life as a tiny, subatomic jiggle in a vacuum. We are not living in a universe that contains a vacuum. We are living inside a vacuum that has been inflated many, many times. We are the frozen scars of a vacuum that once fluctuated so violently it birthed 100 billion galaxies. Look at your hand again. The atoms that make up your skin were once just a collection of these virtual particles that forgot to disappear. We are the debris of an ancient annihilation, the 1/100000% of something that survived when the rest of the matter and antimatter in the early vacuum cancelled each other out. We are the leftovers of an unimaginable explosion that happened because nothing couldn't stay still. But if the vacuum is a field of potential that requires a loan of energy to create matter, we are left with a massive law gap that most videos ignore. If the universe is a quantum fluctuation, what exactly is it fluctuating in? A fluctuation implies a medium, a set of rules, and a field that was already there before the Big Bang occurred. We are not asking how the fire started. We are asking who built the fireplace and wrote the laws of thermodynamics that allowed the wood to burn. To find the answer, we have to look at the most perfect mathematical symmetry ever discovered, a symmetry that suggests our universe might actually be a mirror image of something else entirely. The investigation into the nothing is only getting deeper. The investigation into the nothing in your room has led us to a startling realization. The void is not a silent stage, but a seething ocean of potential. However, this raises a complication that is perhaps more disturbing than the idea of a bubbling vacuum. If the nothing is truly alive with particles popping in and out of existence, why is the universe we see made of something at all? To answer this, we have to look at the ledgers of reality and realize that nothing might just be a state of perfect mathematical balance that was accidentally broken. This is not speculation. This is what the data from our most advanced particle colliders tells us. To understand how nothing can be a mask for everything, we must look at the story of one of the most gifted and unusual minds in the history of science. In the early 1920s, a quiet, intensely focused boy attended Bishop Road Primary School in Bristol. His name was Paul Dirac. He was a boy of so few words that his friends jokingly defined a unit of measure called a Dirac, the smallest number of words it is possible to speak in an hour while still being part of a conversation. Interestingly, he shared that same school hallway with another student who would go on to conquer Hollywood under the name Cary Grant. But while Grant was learning to master the art of the persona, Dirac was learning to see the universe in a way no one else could. He didn't just use math, he visualized it as a geometric architecture. By 1928, physics was facing a crisis of identity. On one hand, we had Albert Einstein's special relativity, governed by the famous E equals mc squared, which described the world of the very fast. On the other, we had the new rules of quantum mechanics, which described the world of the very small. The problem was that these two pillars of reality refused to speak the same language. When you tried to calculate the behavior of a tiny electron moving near the speed of light, the math would break. Dirac, the visualizer, decided to bridge this gap. He sat down and produced a single equation that attempted to marry Einstein's relativity with the quantum world. Today, this is known as the Dirac equation. It is a small collection of symbols that mathematicians describe as profoundly beautiful, a compressed poem of logic. But the equation was smarter than the man who wrote it. It gave back more than he put in. When Dirac looked at the results, he found something that seemed like a mathematical error. The equation had two sets of solutions. The first described the electron we all know, the one currently powering your screen. But the second set described something that shouldn't exist, a particle exactly like the electron, but with a negative energy state and an opposite electric charge. This was the prediction of antimatter. Dirac realized that for every particle of matter in the universe, there is a mirror image with opposite properties. If a particle of matter is a 1, then antimatter is a -1. And as any schoolchild knows, when you add 1 and -1, you get exactly 0. This is the key to the mirror problem. Nothing is not a lack of things. It is a state where matter and its mirror image have perfectly cancelled each other out. Imagine our box of nothing again. We once thought it was empty. Then we learned it was full of quantum seethe. Now, thanks to Dirac, we understand that the seethe is a dynamic dance of pairs. Every time a particle pops out of the vacuum, its antiparticle twin pops out with it. They exist for a trillionth of a second and then they find each other. When matter and antimatter touch, they don't just bounce off one another. They instantly annihilate, turning 100% of their mass back into pure energy. They disappear, returning their loan of energy to the vacuum. The vacuum in your room is effectively a place where matter is constantly trying to exist, but is being immediately cancelled by its own mirror reflection. The nothing is a state of perfect symmetry. But here is the massive complication, the law gap that haunts modern cosmology. If the Big Bang was born from a vacuum fluctuation, it should have produced equal amounts of matter and antimatter. The symmetry should have been absolute. Think about the implications. In the first fraction of a second, as the universe exploded from a point smaller than an atom, trillions of particles of matter and antimatter should have been created in a perfect 1-to-1 ratio. They should have instantly turned back into light, leaving behind a universe that was nothing but a cold, empty bath of radiation. There should be no stars, no galaxies, and certainly no one here to ask why they don't exist. The nothing should have won. But as you look at your hands or the stars in the sky, you are looking at evidence of a cosmic crime. We exist because, for some unknown reason, the symmetry was not perfect. This is not speculation. The data shows that for every 1 billion particles of matter and antimatter that annihilated each other in the early universe, one single particle of matter was left behind. We and everything we see across 94 billion light-years of space are the debris of that 1/100000th of a percent mistake. We are the leftovers of an unimaginable explosion that nearly wiped everything out before it could even begin. If the cancellation had been perfect, the nothing would be absolute. But because of a tiny microscopic imbalance, a scar was left in the void. This leads us to a deeper, more disturbing mystery that most videos ignore. Why did that 1/100000th fail to cancel? Was it a random statistical fluke, or is there a blueprint or information DNA written into the vacuum that preferred matter over its mirror image? If nothing contains the rules of reality, then it seems nothing had a preference for us to exist. As we look deeper into the nothing in your room, we are no longer looking for an absence. We are looking for the instruction manual that broke the mirror and allowed the first light to survive. To find it, we have to look at the zero-energy equation, a mathematical proof that suggests the entire universe might still be nothing even as we speak. The investigation into the rules of the void is only just beginning. We have spent our journey so far peeling back the layers of the nothing in your room, discovering that it is a physical substance we can weigh and a seething ocean of virtual particles. But this discovery brings us face to face with a paradox that seems to break the most fundamental rule of our reality, the law of conservation of energy. If you look at the stars, the galaxies, and even the person sitting in your chair right now, you are looking at an immense amount of stuff. In a universe where you cannot get something for nothing, where did the energy for all this matter come from? This is the zero-energy equation, a mathematical proof that suggests the answer is both simpler and more unsettling than we ever imagined. It suggests that even now, with all its light and fury, The total energy of the universe is exactly zero. To understand how this is possible, we have to look at a moment in 1973 that changed the course of modern cosmology. It didn't happen in a high-tech observatory or a particle collider, but during a routine lecture in New York. The speaker was Dennis Sciama, a man often called one of the fathers of modern cosmology. In the middle of his talk, there was a brief, thoughtful pause. Out of the silence, a young physicist named Edward Tryon suddenly heard himself speaking. He said, almost without thinking, "Maybe the universe is a vacuum fluctuation." There was a murmur of laughter in the room. To the scientists gathered there, the idea sounded like a joke, a clever bit of wordplay. But Tryon wasn't joking. He spent the next few months obsessively unpacking the mathematics of that spontaneous thought. And in December of that year, he published a paper that would eventually redefine our origin story. He realized that if you look at the cosmic ledger, the total accounting of everything in existence, the math doesn't just suggest the universe came from nothing, it demands it. Think about the energy in your room right now. You are surrounded by positive energy. Every atom in your body, every photon of light from your screen, and every bit of heat in your coffee is a form of energy. We know this because of Albert Einstein's most famous equation, E equals mc squared. This equation tells us that mass and energy are just two different ways of saying the same thing. To create the 100 billion galaxies we see in the sky, you would need an amount of positive energy so vast that the number is essentially meaningless to the human brain. If the universe started with zero energy, then creating even a single atom would be a violation of the laws of physics. It would be like trying to buy a house when your bank account has a balance of zero. But Edward Tryon realized there is a second type of energy that we often overlook because we can't see it or feel it directly. This is the energy of the gravitational field. In physics, gravity is a unique force because it is always attractive. It always pulls things together. Because of this, gravitational energy is mathematically negative. This sounds like a theoretical abstraction, but you can feel the reality of it with a simple domestic analogy. Imagine you are holding a heavy book in your hand. To lift that book away from the floor, you have to use your own energy. You are doing work against the pull of the earth. The higher you lift the book, the more energy you have put into the system. But if you let the book go, that energy is released as it falls back down. In this sense, the gap between the book and the floor represents a debt of energy. To pull things apart against the pull of gravity requires a deposit of positive energy, which means the state of being pulled together, the gravitational field itself, is a withdrawal. It is negative. This is not speculation. This is what the data says. When you add up all the positive energy of the matter in the universe, and the stars, the planets, the black holes, and then you add up all the negative energy of the gravitational fields pulling those objects together, something remarkable happens. They appear to cancel each other out perfectly. The total is zero. This is the zero-energy universe hypothesis, and it is a mathematical necessity for a universe born from a vacuum. If the total energy of the cosmos is zero, then the law of conservation of energy has never been broken. The universe didn't require a source or a creator to provide the energy for the Big Bang because, in a very real sense, no energy was ever actually used. We are like a bank account that has $1 million in credits and exactly $1 million in debt. On the surface, it looks like a fortune, but the net balance is nothing. This brings us back to Heisenberg and the quantum seed. As we discussed, the uncertainty principle allows the vacuum to borrow energy from the future to create virtual particles, provided it pays that energy back almost instantly. The more energy it borrows, the faster the loan must be repaid. If you borrow enough energy to create a single electron, you have to pay it back in a fraction of a second so small that light can't even cross an atom in that time. But Tryon realized there is a loophole. If you create a universe where the total energy is exactly zero, the loan from the vacuum never has to be repaid. If the debt is zero, the duration of the loan becomes infinite. Our 13.8 billion-year-old universe might simply be a quantum fluctuation that, because it perfectly balanced its matter against its gravity, has managed to last for an eternity without the auditor of physics noticing the debt. This is a deeper layer of the mystery that most videos miss. We often ask, how did something come from nothing? But the zero-energy equation suggests that we are asking the wrong question. The real mystery is not how something was created, but how nothing was rearranged to look like us. We are not a something that replaced nothing, we are a specific, complex configuration of nothing. Imagine a flat, still lake. That is the vacuum in a state of perfect balance. Now imagine you reach into the water and pull up a wave. To create the peak of the wave, Arto, you must simultaneously create a trough, the age Arto. From a distance, the lake still contains the same amount of water it always did. The total displacement is zero. But for a brief moment, to an observer standing on the surface, there is a visible structure. There is a something where there used to be a nothing. Right now, you are that wave. Every cell in your body is a peak of positive energy balanced by a trough of gravitational debt. This is confirmed science. Multiple independent teams have measured the flatness of the universe, the specific density of matter and energy, and found that it is remarkably close to the critical value required for the total energy to be zero. If the universe were even slightly different, if there were more matter than gravity, or more gravity than matter, the cosmos would have either collapsed instantly or flown apart so fast that stars could never have formed. The fact that we are here to measure the vacuum is proof that the balance is nearly perfect. But this leads to a disturbing implication that haunts the edges of our data. If the universe is a zero-sum fluctuation, then our entire existence is a temporary state. We are a long-lived bubble in the void. And just as virtual particles eventually annihilate and return to the vacuum, our universe may one day realize its debt. If the balance of dark energy and gravity shifts, if the zero-energy equation is ever slightly disturbed, the wave could collapse back into the still lake of the vacuum. As you sit in your room, feeling the stillness, you are actually participating in this grand mathematical balance. You are not just standing on the earth, you are part of a cosmic ledger that is trying to remain at zero. But if nothing is so perfectly balanced, why is it so messy? Why do we see the scars of the Big Bang written across the sky? To see the physical evidence of this cosmic birth, we have to look at the oldest light in the universe, a baby scan of the cosmos that shows us exactly where the vacuum began to freeze. The investigation is moving from the math of the void to the physical image of our beginning. The investigation continues. To understand why the vacuum of the early universe matters to you personally, we have to move past the mathematical proofs of the zero-energy equation and look at the physical evidence written across the sky. We are moving from the abstract nothing into the world of hard data, a realm where we can actually see the blueprint of our own beginning. For decades, the birth of the universe was a story we told ourselves using equations, but in the mid-20th century, we accidentally stumbled upon the baby scan of the cosmos, a relic image that confirms everything we have discussed about the seething void. This is not speculation, this is the oldest light in existence, and it has been traveling through the darkness for 13.8 billion years just to reach your eyes today. The discovery of this evidence began in 1965 with a persistent, annoying hiss. Two physicists at Bell Labs, Arno Penzias and Robert Wilson, were trying to use a large horn antenna in New Jersey to detect radio waves from the Milky Way. But they kept hearing a background noise that they couldn't explain. It was a faint, steady microwave static that came from every single direction in the sky, day or night, regardless of where they pointed their antenna. At first, they thought it was terrestrial interference, perhaps the nearby lights of New York City, or even white dielectric material, which was their polite scientific term for pigeon droppings inside the horn. They meticulously cleaned the antenna and ruled out every possible local source, yet the hiss remained. What they had actually discovered was the echo of the Big Bang, the cosmic microwave background, or CMB. This light is the thermal radiation left over from the fiery birth of our universe, but to understand why it is a baby scan, you have to understand the state of the nothing 380, 00 years after the beginning. Before this moment, the universe was not a vast transparent expanse. It was a hot, opaque soup of particles. It was so dense and energetic that atoms could not yet hold together. Light, photons, tried to travel through this soup, but they were constantly being scattered by free-roaming electrons like a beam of a flashlight hitting a thick, impenetrable wall of fog. For the first few 100,000 years, the universe was essentially a foggy, blinding, white void. But as the universe expanded, it cooled. At exactly 380,000 years post-Big Bang, the temperature dropped to about 3,000 degrees Kelvin. At this recombination epoch, the free electrons were finally moving slowly enough to be captured by atomic nuclei, forming the first neutral atoms. Suddenly the fog lifted, the electrons were tucked away inside atoms, and the light that had been trapped for eons was suddenly free to travel through space. This is the first light, and because the universe has been expanding ever since, that light has been stretched into the microwave range, cooling down to a temperature of just 2.7 degrees above absolute zero. When you look at a map of the CMB produced by modern satellites like Planck or WMAP, you aren't just looking at a pretty picture, you are looking at a baby scan of the universe at 12 hours old compared to a 50-year-old adult. This is established science. The data from these satellites has mapped the temperature of this light to a precision of 1 part in 100,000, and what we see in that scan is a speckled pattern of tiny, microscopic variations in temperature, red spots that are slightly warmer and blue spots that are slightly cooler. These variations are the scars left by the vacuum. This brings us to the most profound and unsettling connection between the nothing and the everything. Remember the quantum seethe we discussed earlier, the bubbling soup of virtual particles and fluctuations that exist in a vacuum? Most competitors treat these fluctuations as subatomic trivia, but the CMB data shows they are the very reason you are here. During the first fraction of a second, the universe underwent inflation, a period of exponentially fast expansion where space doubled and doubled in size at speeds far beyond the speed of light. Inflation took those tiny, microscopic jiggles in the vacuum, objects smaller than an atom, and stretched them across the entire sky. These fluctuations were frozen into the fabric of space by the sheer speed of the expansion. They became density variations in the primordial gas, hills and valleys in the distribution of matter. A region that had a slightly higher energy fluctuation became a hill of gravity, drawing in more and more matter over billions of years. These frozen quantum fluctuations are the seeds of the cosmic web. Every galaxy you see in the deep field images, including our own Milky Way with its 100 billion stars, began its life as a subatomic jiggle that forgot to disappear because it was caught in the runaway expansion of the void. This is the superior insight that changes how you should view the cosmos. You are not looking at a universe that contains matter. You are looking at the scars left by a vacuum that once fluctuated so violently it birthed galaxies. We are the debris of an ancient annihilation, the 1/100000% of matter that survived when the rest of the early vacuum's potential cancelled itself out. The DNA of the entire universe, the blueprint for where every star and planet would eventually form, was written into the nothing before the first atom even existed. Look at your hands again and realize that the atoms within them were seeded by these specific blue and red spots on the baby scan. This is confirmed by the data. When physicists use the mathematics of Werner Heisenberg and Paul Dirac to calculate how these fluctuations should look, the results match the real-world pictures from the Planck satellite to an accuracy of 1 part in a million. The speckled pattern across the sky is not random noise, it is the physical information blueprint of your existence. However, presenting this data reveals a deeper, more disturbing complication that the standard models struggle to explain. If the nothing was a chaotic soup of random fluctuations, then the CMB scan should look like absolute chaos, like a balloon filled with paint that has been burst against a wall. But the data shows something else. The universe is remarkably uniform. Regions of the sky that are 94 billion light-years apart today have almost exactly the same temperature, even though they are so far apart that light has never had time to travel between them to balance their heat. This is the horizon problem, and it implies that something or some rules governed the nothing before it even started expanding. The CMB scan has given us a picture of our embryo, but it has also revealed anomalies that shouldn't exist. In 2024, researchers discovered structures like the Big Ring, a ring-shaped pattern of galaxies spanning 1.3 billion light-years. This structure is so massive and so organized that it defies our current understanding of how small quantum fluctuations could grow. It suggests that the nothing from which we were born might have had a pre-existing architecture or a previous history that we are only just starting to glimpse. As you sit in the stillness of your room, you are surrounded by the fossil imprints of these ancient events. The microwave background radiation is passing through your body right now. If you could see in the microwave spectrum, the entire sky would glow with the fading heat of the Big Bang. We have seen the scan, and we have measured the scars, but to understand what triggered the seethe to expand in the first place, we have to move beyond our single bubble of space. We have to consider that our Big Bang might not have been a creation from nothing, but a collision between two pre-existing realms of reality. The investigation is shifting from the map of our sky to the higher dimensional sea in which our universe might be floating. The investigation continues. We have looked at the maps of our sky, the ancient speckled baby scan of the cosmic microwave background, and we have seen the frozen scars left by a vacuum that fluctuated 13.8 billion years ago. We have established that the nothing in your room is not empty, but a high-pressure reservoir of potential energy, a seething ocean that birthed everything we see. But this discovery pushes us into a corner. If the Big Bang was a quantum fluctuation, what was it fluctuating in? A jiggle requires a medium. A wave requires a surface. This is the massive law gap in the standard narrative. We are told the universe came from a vacuum, but we are rarely told what holds that vacuum in place. To answer this, we have to shift our scale one final time. We have to move beyond the subatomic and even beyond the 3 dimensions of space you can see around you. We have to consider the possibility that our entire universe is not an isolated bubble, but a single sheet of reality floating in an 11-dimensional sea. This is the transition from quantum field theory to M theory, the master theory that attempts to unify all the forces of nature. To understand the scale of what we are discussing, you must first acknowledge the limits of your own perception. Right now, you perceive the world in 3 dimensions of space: up, down, left, right, forward, back, and 1 dimension of time. This feels like the total sum of existence. But this is a biological filter. This is what the data from our most advanced mathematical models says. the universe may require at least 7 additional spatial dimensions that are invisible to our eyes. Imagine you are looking at a single sheet of paper floating in the middle of your room. To a microscopic organism living on the surface of that paper, the entire universe is 2-dimensional. They can move left, right, forward, and back, but they have no concept of up or out. They are unaware of the vast volume of the room surrounding their sheet. In the language of M-theory, our entire 4-dimensional spacetime, everything from the farthest galaxy to the atoms in your coffee, is just such a sheet. Physicists call these sheets branes, short for membranes. This is not speculation, it is a mathematical necessity for the equations of string theory to remain consistent. This realization redefines the nothing in your room in a way that is personally implicating. If our universe is a brane, then the nothing you see between your eyes and this screen is not an empty void extending to infinity. It is a boundary. It is the surface of our sheet. And just as 2 sheets of paper can be placed nearly on top of one another in a 3-dimensional room, another brane, another entire universe with its own stars, its own light, and its own laws of physics could be floating just a fraction of an inch away from you right now. You cannot see it because it is up or out in a direction your brain cannot process. You are separated from this other reality not by distance, but by a dimension. This brings us to the brane collision, a theory known as the ekpyrotic model, which offers a radical alternative to the standard Big Bang story. In the traditional view, the Big Bang is a singular moment of creation from a point of infinite density. It is an event that has no before because time itself started at that moment. But if we accept the existence of these higher dimensional branes, the Big Bang becomes something much more mechanical. It becomes a collision. Imagine 2 of these sheets floating in the 11-dimensional bulk, the vast empty sea of higher dimensional space. These branes are not static. They are governed by gravity and other forces that act across the dimensions. Over trillions of years, these 2 sheets may be drawn toward each other. They drift through the nothing of the bulk, 2 empty, cold, and desolate expanses. But as they get closer, the energy between them begins to build. When they finally touch, the result is not a silent contact, but a cosmic clapping of unimaginable power. At the point of contact, the kinetic energy of the collision is instantly converted into the heat and matter of a Big Bang. This is the cosmic spark. In this model, the Big Bang was not the beginning of time or space. It was the moment the energy from a higher dimension was dumped into our 3D sheet. It redefines the vacuum fluctuation not as a random jiggle in a single field, but as the friction caused by 2 pre-existing nothings rubbing against each other. This is a superior explanation for the horizon problem we discussed in the previous chapter. Remember the mystery of why the universe is so uniform, why regions billions of light-years apart have the same temperature. In the standard model, we need inflation, a mysterious, faster-than-light expansion, to smooth everything out. But in the brane collision model, the uniformity is natural. The 2 sheets were already flat and smooth before they collided. When they hit everywhere at once. The Big Bang didn't happen at a single point. It happened across the entire surface of our reality simultaneously. This is confirmed by the mathematical reasoning behind M-theory. The nothing of the bulk acts as a stabilizer. It is the fireplace in which the fire of our universe was lit. If this is true, it means that nothing is not just a sea of virtual particles. It is a multi-layered structure of sheets and voids. We are not living in the only universe. We are living on one of many membranes that occasionally collide, spark into life, and then drift apart again. But there is a deeper, more unsettling layer to this shifting scale. If the Big Bang was a collision between 2 branes, then Our universe might be part of an eternal cycle. After the collision, the brains move away from each other. Our universe expands, stars form, and eventually, after trillions of years, the energy fades, and the universe becomes cold and empty once again, a nothing sheet. But gravity in the higher dimensions may eventually draw the sheets back together for another touch. This is the ekpyrotic cycle, a slow, rhythmic breathing of the cosmos. Think about what this means for the stillness of your room. You are not just standing on a planet. You are a passenger on an 11-dimensional membrane that is currently drifting through a void of unimaginable proportions. The nothing you perceive is merely the limit of your three-dimensional vision. In reality, you are part of a cosmic interface. We are the sparks that were created when two higher dimensional voids touched for a fraction of a second. However, moving to the scale of the multiverse reveals a new complication that haunts the edges of our data. If our universe is a sheet and the nothing is just the space between sheets, what determines the information written on each sheet? If nothing is truly zero, how does it decide that this specific collision would produce the laws of physics that allow for carbon, oxygen, and life? This leads us to the information conservation paradox. If the universe is a projection or a spark from a higher dimension, then the nothing must be more than just a reservoir of energy. It must be a reservoir of data. It must contain the blueprint for every galaxy and every mind that has ever existed. To find this blueprint, we have to look at the holographic principle, the idea that our 3D world is just a projection of information stored on a 2D surface at the edge of the void. We are no longer asking how the universe was born. We are asking what is recording the data of its existence. The investigation is moving from the collision of sheets to the very screen upon which our reality is projected. The investigation continues. We have moved from the scale of the ocean of air surrounding your body to the subatomic bubbling of the vacuum, and finally to the 11-dimensional collisions of membranes in a higher dimensional sea. We have seen how nothing provides the energy, the space, and the triggers for our existence. But this leads us to a deeper, more unsettling complication, the most profound law gap in our understanding of the void. If the universe was born from a vacuum fluctuation, how does that nothing contain the complex blueprint for everything you see? How does a silent, empty void store the specific instructions required to build 100 billion galaxies, the specific weight of an electron, and the neural architecture of your own brain? To answer this, we have to look at the possibility that matter, energy, and even space itself are not the fundamental building blocks of reality. Instead, we must consider the idea that the universe is a decryption, a three-dimensional projection of information stored on a two-dimensional surface at the very edge of the void. This is the holographic principle, and it suggests that the nothing you see in your room is not a stage, but a screen. To understand why this is not speculation, but a mathematical necessity, we have to look at a paradox that emerged from the most extreme environments in the universe, black holes. In the 1970s, a young physicist named Jacob Bekenstein began to wonder what happens to information when it falls into a black hole. Imagine you take a library of books, millions of pages of data, history, and poetry, and you throw them into the abyss. In the classical view of physics, that information is simply destroyed. But in the quantum world, there is a fundamental rule. Information can never be lost. If you were to burn a book in your fireplace, the information isn't gone in a mathematical sense. It is simply scrambled into the smoke, ash, and heat. In theory, if you were a god with infinite computing power, you could reconstruct the book from the debris, but a black hole seemed to be a cosmic shredder that destroyed the information entirely. Bekenstein discovered something that shocked the scientific community, and broke our intuition about space. He realized that a black hole has entropy, a measure of the information it contains. In every other physical system in your room, the amount of information it can hold is proportional to its volume. If you have a box, and you want to know how many atoms you can fit inside, you look at the 3D space within the walls. But Bekenstein's math showed that for a black hole, the information capacity is proportional to its surface area, not its volume. This is confirmed science. The data of everything that falls into a black hole is written bit by bit onto the two-dimensional surface of the event horizon. Think about the implications of that discovery for the room you are in right now. Imagine you have a bookshelf. You would assume the number of books you can fit depends on the depth and height of the shelves. But the physics of the vacuum suggests that the total information in your room is actually limited by the area of the walls, the floor, and the ceiling. It is as if the stuff inside the room is just a three-dimensional shadow of data that is actually stored on the boundaries. This was the birth of the holographic principle developed by Leonard Susskind and Gerard 't Hooft. They realized that if a black hole, the most dense object in the vacuum, works this way, then the entire universe might work this way too. This is the deeper layer of the mystery. Our 3D reality might be a projection. This is not a metaphor, it is what the mathematical data from the ADS/CFT correspondence tells us. This theory, proposed by Juan Maldacena in 1997, provides a concrete framework where a gravitational theory in a higher dimensional space is perfectly equivalent to a quantum theory in a lower dimensional space. It suggests that everything you experience, the feeling of the chair beneath you, the depth of the sky, the passage of time, is an emergent phenomenon. We are like the characters in a high-definition video game. To us, the world feels three-dimensional and solid, but the actual data, the code that defines our existence, is sitting on a flat, 2D hard drive at the edge of the observable universe. If the universe is a hologram, then our definition of nothing must change once again. In this framework, the vacuum is not a void, and it is not just a field of energy. The vacuum is the screen upon which the data of the cosmos is projected. This redefines the Big Bang not as a chaotic explosion of matter, but as a decryption. Before the Big Bang, the information state of the universe was in its most compressed form, a zero state where the code was written but not yet run. The nothing was actually a highly compressed information state, containing the DNA of every star that would ever burn. When inflation occurred, it wasn't just space that expanded, it was the screen itself that grew, allowing the information to be projected at a cosmic scale. You can visualize this with a domestic analogy. Think of a common credit card. On its surface, there is often a small silver hologram. When you tilt it in the light, a 3D image of a bird or a globe appears to float in space. That image has depth, shape, and detail, yet you know that all the information required to create that 3D experience is stored on the 2D silver film. If you were to scratch the film, the 3D image would distort. In this investigation, we are the 3D image, and the vacuum is the silver film of the universe. The reason nothing feels so heavy and seething is because it is carrying the massive bandwidth of reality itself. This leads us to a disturbing realization about the stillness of your room. If the 3D world is a projection, then the distance between you and the wall is an illusion created by the way the information is organized. This is why quantum entanglement, what Einstein called spooky action at a distance, is possible. If two particles are entangled at opposite ends of the universe, they can influence each other instantly because on the 2D hard drive at the edge of space, those two particles are actually right next to each other. The space between them is just a trick of the projection. This is not speculation. It is one of the most accurate descriptions of the natural world we have, matching experimental results to 1 part in a million. But this raises the most profound question of all. If our reality is a projection of information, what is recording the data? Information is a physical thing. It has weight, and it requires a medium. If the universe is a hologram, then nothing is the most sophisticated storage device ever conceived. It suggests that the void is not the absence of things, but the unprojected state of everything. This is a superior insight that changes your place in the cosmos. You are not a collection of atoms wandering through a void. You are a specific, complex data point being processed by the vacuum. Look at the baby scan of the universe we discussed earlier, the cosmic microwave background. Most videos see it as a map of heat, but through the lens of the information blueprint, we see it as the boot-up sequence of the cosmic computer. Those tiny red and blue spots are not just temperature variations, they are the initial bits of data being written onto the screen of the vacuum. Every star and galaxy that formed afterward was simply the result of that data being processed and decrypted over billions of years. We are living inside a calculation that began in the nothing. As you sit in your room, feeling the solidness of the world, you are actually participating in this holographic projection. You are the only part of the data that has developed a mind to look back at the screen and ask how the movie began. But the movie is reaching a point where the data suggests a final, terrifying possibility. If the universe is a projection of information, what happens when the information reaches its limit? What happens if the nothing from which we came is not a beginning, but a transition, a cycle that has happened before and will happen again? To understand our ultimate fate, we have to look at the eternal cycle, the idea that our nothing is actually the end of a previous universe that became so thin and cold it looked exactly like a new beginning. The investigation is moving from the screen of the hologram to the clock of the cosmos. The investigation continues. We have followed the data from the seething vacuum in your room to the speckled maps of the first light, and even into the 11-dimensional collisions of higher reality. But every path we have taken eventually hits a wall. Whether it is a quantum fluctuation or a brain collision, we are still left with the same unsettling question. Where did the nothing come from in the first place? To answer this, we must consider a possibility that is more radical than a single moment of creation. We must entertain the idea that our beginning was not a start at all, but a transition, a bridge between our world and a previous existence that has long since faded into silence. This is the realm of the eternal cycle, and it suggests that the nothing from which we were born was actually the cold, exhausted end of a universe that existed before our own. To understand this, we must look at the work of Sir Roger Penrose, a man who sees the universe not as a collection of particles, but as a masterpiece of geometry. Penrose is not a fringe theorist. He is a Nobel laureate who spent decades working alongside Stephen Hawking to prove that singularities are an inevitable outcome of gravity. But as Penrose looked at the ultimate fate of our universe, he noticed a mathematical symmetry that everyone else had ignored. He realized that the distant, unimaginably cold future of our cosmos bears a haunting, identical resemblance to the hot, dense state of the Big Bang. This is conformal cyclic cosmology, or CCC, and it suggests that our universe is just one aeon in an infinite chain of rebirths. Think about the future that the current data predicts for our world. Because the expansion of the universe is accelerating, driven by the mysterious force we call dark energy, galaxies are flying away from us faster and faster. In a few trillion years, the sky will go dark, Every galaxy beyond our local group will have moved beyond our cosmic horizon, their light unable to reach us. Stars will exhaust their nuclear fuel and fade into black dwarfs. Eventually, even the black holes will evaporate through Hawking radiation, turning their massive bulk back into a thin, cold bath of photons. This is the heat death of the universe, a state of maximum entropy where no more work can be done, no more stars can be born, and no more minds can exist. Most cosmologists see this as the absolute end, the graveyard of reality. But Penrose noticed a loophole in the physics of this dark future. In a universe where all matter has decayed and only light remains, the concepts of size and time lose their meaning. Photons, being massless, do not experience time. To a photon, there is no difference between a second and a billion years. Furthermore, without matter to provide a reference point, no atoms to use as rulers, no clocks to measure a beat, the universe forgets how large it is. This is scale invariance. This is confirmed by the mathematics of conformal geometry. In a universe containing only massless particles, a vast, infinite and cold expanse is physically and mathematically identical to an infinitely small, hot and dense point. When the universe becomes thin enough and cold enough, it effectively resets. The nothing of the far future becomes the nothing of a new beginning. The end of the previous aeon becomes the Big Bang of the next. This means that the nothing we have been investigating, the seething vacuum in your room, is actually the information blueprint of a universe that died billions of years before our own. We are not a creation from an empty void. We are the decryption of the leftovers. But if this is true, we should be able to find evidence of that previous world. We should be able to see fossil imprints that survived the transition from the old aeon into ours. This is not speculation. Penrose claims that the massive gravitational events of the previous universe, the collisions of supermassive black holes, would have sent ripples through the fabric of space that would still be visible in our sky today. He calls these Hawking points, concentric circular patterns of energy that should appear in the cosmic microwave background. While most of the scientific community remains skeptical, arguing that these patterns might just be random noise, a series of recent discoveries has forced us to look again. In 2024, researchers discovered a structure that defies every rule of standard cosmology. They call it the Big Ring. To understand the scale of the Big Ring, you have to look past the stars of our own galaxy. It is a ring-shaped pattern of galaxies and galaxy clusters spanning 1.3 billion light-years in diameter. It is so large that if you could see it with the naked eye, it would appear 15 times wider than the full moon in your night sky. This is a leviathan on the cosmic stage. According to the standard cosmological principle, which states that the universe should be smooth and uniform on such large scales, the Big Ring simply shouldn't exist. It is too large and too organized to have grown from the tiny quantum fluctuations we see in the baby scan of the early universe. One researcher, Alexia Lopez, noted that this structure defies explanation using our best current theories. It is like finding enormous tracks pressed into the sand of a desert and being able to measure the stride length and the depth, but having no idea what creature could have made them. But through the lens of Penrose's eternal cycle, the Big Ring makes sense. It could be the frozen scar of a gravitational event that happened in the aeon before ours, a ghost of a structure that was so massive it survived the reset and was written into the blueprint of our vacuum. This leads us to a state of honest uncertainty. We are standing at the very frontier of what science can tell us. We have two competing stories. One says that the universe had a singular, absolute beginning 13.8 billion years ago and will eventually fade into a permanent, silent nothing. The other says that we are part of an infinite, rhythmic breathing of the cosmos, where nothing is just the moment we catch our breath before starting again. The data for the eternal cycle is tantalizing, but it is not yet definitive. It is, as some physicists have described, like watching a noble animal struggle against the limits of its own cage. We want to believe in the cycle because it provides a sense of continuity, a way to escape the cold finality of the heat death. It suggests that our existence is not a one-time statistical fluke, but a necessary chapter in a book that has no first page and no last. But we must be careful not to mistake our desire for meaning for the data itself. The Big Ring and the Hawking points are anomalies. They are the hiss in the radio antenna that we are still trying to clean. They might be the proof of a previous universe, or they might be hints of new physics we haven't yet named. They might be cosmic strings, ultra-thin defects in space-time, or they might be evidence of multiple mini-bangs, a theory proposed by Dr. Richard Liu in 2025, which suggests the universe's expansion is driven by sudden bursts of matter and energy entering our reality at different times. As you sit in the stillness of your room, you are witnessing the forward momentum of this investigation. We are the generation that is building the instruments, the James Webb Space Telescope, the Dark Energy Spectroscopic Instrument, that are finally peering into these gaps. We are finding more bright, early galaxies than our models predicted, discovering that galaxies like JADES-GS-Z14-0 were already fully formed just 280 million years after the Big Bang. We are seeing that the universe grew faster and more efficiently than we ever imagined. This suggests that our understanding of time zero is incomplete. We are realizing that the nothing was not a blank slate, but a fertile ground of possibilities. Whether we are a fluctuation in a vacuum, a collision of brains, or a link in an eternal chain, one thing is certain. The nothing is much more sophisticated than we were taught. It carries the weight of an ocean, the energy of a billion suns, and the memory of everything that came before. We are left with a final, human-scale reflection. If the universe is a cycle, then the atoms in your coffee, the air in your lungs, and the neurons in your brain are made of recycled nothing. You are not just a spectator to this mystery. You are the physical evidence of its survival. You are the only part of the void that has woken up to ask where the rest of it went. But there is one final layer to the architecture of nothingness, the most disturbing and high-retention question of all. If the vacuum is a field of potential governed by laws, and if those laws were written into the nothing before the first light ever shone, who or what was there to observe the first fluctuation? In quantum mechanics, a wave function of probabilities only collapses into a real state when it is observed. If the entire universe began as a quantum fluctuation in a void, then for that fluctuation to become something, it may have required a mind to see it. The investigation is moving from the clock of the cosmos to the most intimate mystery of all, the relationship between the nothing and the mind. We are about to ask if the universe created us, or if we, in some strange mathematical way, created the universe. The investigation concludes in the final chapter. You are back in your room now, and the stillness has returned. The coffee in your cup is cold, the air is silent, and the walls appear as solid and dependable as they did when our investigation began. But your perspective of this space has been fundamentally altered. You now know that the nothing between your hand and the table is a high-pressure reservoir of potential energy, a seething ocean that birthed everything you see. You understand that you are standing on a three-dimensional membrane drifting through an 11-dimensional sea, and that your very body is a collection of frozen quantum scars left behind by a vacuum that fluctuated billions of years ago. But as we reach the end of this journey, we must confront a final, deeper complication that most narratives ignore, a mystery that places you, the observer, at the very center of the cosmic ledger. This is the consciousness trigger, and it suggests that for the nothing to ever become something, it may have required a mind to make it real. To understand why your presence in this room is a mathematical necessity, we must return to the rules of the very small. As we have seen, the quantum world is not a place of certainties, but of probabilities. According to the wave equation written by Erwin Schrödinger, an electron is not in a single, definite place. Instead, it is fuzzy and spread out, described by a wave function that represents every possible location it could occupy. In the early 20th century, physicists realized that these particles only choose a specific state when they are measured or observed. This is the collapse of the wave function, the moment when a cloud of possibilities crystallizes into a single physical reality. This is not speculation. It is one of the most accurately measured phenomena in the history of science. This leads us to a massive law gap in the story of our origins. If the entire universe began as a subatomic quantum fluctuation, an object smaller than an atom governed by the laws of uncertainty, then, at time zero, the cosmos existed only as a wave function of nearly infinite probabilities. It was a superposition of every possible universe that could ever exist. According to the strict rules of quantum mechanics, such a system should remain as a cloud of maybe forever unless it is observed. This creates a profound paradox. If there were no minds, no eyes, and no observers during the first trillionth of a second, how did the vacuum fluctuation ever collapse into the solid, structured universe we see today? Who or what observed the Big Bang? Some physicists, like Hugh Everett, suggest a radical solution through the many worlds interpretation. He proposed that the wave function never truly collapses. Instead, every possible outcome of that initial nothing actually occurred, splitting the cosmos into an infinite number of parallel universes. In this view, there is a universe where the vacuum never fluctuated, a universe where matter and antimatter cancelled out perfectly, and a universe, this one, where you are currently sitting in your chair. In every possible combination of the laws of nature, a different version of reality exists. We see this specific universe because it is the only one that allows us to exist and ask the question. But this brings us to a more personally implicating layer of the mystery. If the universe is a holographic projection or a decryption of an information state, then it requires an interpreter. Information, by its very definition, is only meaningful if there is a mind to process it. We once thought we were mere spectators to a universe that would exist whether we were here or not, but the data suggests we might be participants. We are the only part of the nothing that has developed a mind, the only part of the void that has woken up to look back at the screen and investigate where it came from. Think about the domestic stillness of your room again. You are not just an accidental collection of atoms. You are the debris of an ancient annihilation, the 1/1000th of a percent of matter that survived the mirror problem. You are the frozen remnants of a vacuum that once fluctuated so violently it birthed galaxies. For 13.8 billion years, the information stored in the nothing has been processing, moving from the simplicity of hydrogen into the complexity of stars, planets, and eventually the neural architecture of your brain. Throughout the history of our species, we have looked for meaning in the stars. Our ancestors, like the Neanderthals, looked at the dawn and believed the sky was made for them, a home provided by creators who were watching over them. As our consciousness matured, we built civilizations and developed technologies to harness the vacuum, yet the misery and pain of our limitations never truly went away. We have often felt small and insignificant against the backdrop of an infinite, silent void, but the superior insight of this investigation is that you are not a small thing in a big universe. You are the universe becoming aware of itself. Meaning is not something you find in the void, it is something you create by the very act of observing it. This is the forward momentum of our species. We are currently in an era of unprecedented discovery, using instruments like the James Webb Space Telescope to peer into the cosmic dawn, and satellites like Planck to map the baby scan of our embryo. We are seeing that galaxies formed faster and more efficiently than our models predicted, suggesting that our understanding of the nothing is still incomplete. We are realizing that dark energy might be evolving, and that the nothing of our future might be very different from the nothing of our past. The investigation is not over. It is accelerating. As you sit in the quiet of your home, you are surrounded by the fossil imprints of these ancient events. The cosmic microwave background radiation, the echo of the first light, is passing through your body right now. Trillions of neutrinos, the ghostly particles of the early universe, are streaming through you without you even feeling a tickle. You are participating in a grand mathematical balance where your matter is perfectly cancelled by gravitational debt, keeping the total energy of your existence at exactly zero. This is confirmed science. This is what the data shows. The mystery of why there is something instead of nothing remains open, but you are no longer a spectator. You are a specific, complex configuration of the vacuum, a long-lived bubble in the void that has been given a brief moment to contemplate the infinite. Whether we are a quantum fluctuation, a collision of membranes, or a link in an eternal chain, you are the participant who makes the story real. The investigation into the rules of the void is only just beginning, and as long as there is a mind to ask the question, the nothing will never be truly empty. You are small, the universe is enormous, and the fact that you can understand the difference is the most interesting thing we know. The stillness of your room is not an absence of activity, it is the silent, ongoing work of the most sophisticated storage device ever conceived. You are part of the ledger, you are part of the blueprint. And as you turn off the lights tonight, remember that the darkness is not empty. It is full of everything we have yet to discover.